Moment of inertia. There are two main applications for moment of inertia. One application is rotational motion. And statics to dynamics, statics solves a lot of problems that are right on the edge of almost moving. So maybe a building is almost tipping over, or the Ferris wheel is almost going to start rotating. And so you start getting into kind of a fuzzy area where you have to think about the motion that's almost going to happen when you're looking at the static scenario too. And that transition from stopped to moving is really important. That's an important spot to look at to analyze systems from. So rotational motion is one application for moment of inertia. The other big application is how hard is it to bend something? And this goes into I-beam designs, pipes. If you take mechanics of materials, you will get into this more in your mechanics of materials class too. So moment of inertia. What comes to mind when you think of the word inertia? What does inertia mean? And then we're going to think about what moment means and put moment and inertia together. So here's inertia. An object at rest tends to stay at rest unless acted upon by an outside force. Here's the full Newton's first law. So everything remains at a state of rest or uniform motion unless acted upon by an external force. To put an equation to this law, and there is so much that can be derived from F equals ma. So for statics, everything we've done in statics, force is not equal to ma. There's no accelerations happening in statics. In statics, forces add to zero. But if the force does not balance, then that unbalanced force creates motion. It creates acceleration. So the equal and opposite reaction does not have to be equal and opposite forces. It can be, the reaction can be a motion and acceleration rather than a force. So we have this F equals ma, and maybe you remember from physics, acceleration is change in velocity over change in time. So when you look at Newton's first law, you're looking at motion that is either staying the same, or what would it take to change the motion of something? Whether to go from rest to having some velocity or changing the velocity of something. And that's the whole point of acceleration, is changing how fast something is moving. Okay, so dv dt, change in velocity over change in time. Take this dt and pull it over to the force side. And what you get, f dt equals mdv. This turns into your linear momentum, mdv, and fdt is impulse. And so with Newton's law, you say an object in motion stays in motion unless acted upon by a force. So here's the motion, mv, and here's the force that is going to change that motion. And it's everything from maybe the car stops, but you don't want to stop, right? So you want to keep traveling at that same velocity, and then it's going to take some sort of a force to slow you down with the car or something. So this is linear momentum. This is traveling in a straight line, something going in the x direction or the y direction or the z direction, but this is the inertia concept. Okay, so here's another example of that. So the truck stops, the rock does not stop. The rock has some linear inertia. An object in motion wants to stay in motion, and it's going to take a force to stop that object from moving. One more. If your impulse, f dt, is 0, then you say that your inertia is conserved, your linear momentum is conserved. So the starting velocity is the same as the ending velocity, and this is usually used to analyze systems of particles where you have internal forces and no external force. Okay, let's add in rotational motion to that inertia concept. So keep that Newton's law, an object in motion wants to stay in motion. What kind of motion is it talking about? There's a lot of different kinds of motion. I can move in the x direction, y direction, z direction. How about rotational motion? and I can rotate around the x-axis. I can rotate around the y-axis or around the z-axis. And so it's more than just linear motion when you're talking about inertia. So something going in circles wants to keep going in circles. You can imagine maybe a spaceship in outer space where there's no friction. And if you start that thing rotating, it's just going to keep rotating and keep rotating and keep rotating. There's examples of that in outer space, right? Okay, so there's more types of motion. And if something is going in a circle like that, what would change that rotational motion? What would make it start spinning faster or spinning slower? What would it take to change rotational motion? And we've already gone through moment. So it's not just going to take a force to change the motion. Just pushing on it with a force, that'll move it in the x direction or the y direction. But to rotate it, you need two different things to rotate it. You need a lever arm and a force that's perpendicular to that lever arm. So those two quantities are going to change the rotational motion of something. Okay, so moment of inertia. So we're going to combine the concepts of moment with thinking about how that moment could change the rotational motion of something. And bending will also come into play here. So it'll change how easily it is to bend something or how easily it is to rotate something. Okay, so lever arm times force, perpendicular distance. If you have kids on a merry-go-round, will it be easier to push this if all the kids are piled up in the center or if the kids are out sitting on the edge of it? Okay, so let's say you have a blindfold on and you're pushing on this and you can't quite see what you're pushing on. You can only feel the resistance to rotating it. Would it be easier, and just think through this intuitively before we crank through the equation, would it be easier to rotate it if the kids are sitting on the edge or if they're sitting in the middle? The next time you go to the park, try this out so that you can actually feel that moment and feel the force that it takes to rotate something. So moment is equal to r cross f. ma is dv dt. I can take this dt over. m dt, this is kind of equivalent to the impulse. So this is what's going to change how fast something is rotating, how fast it's spinning. And here is r cross mv. This is turning into our angular momentum. And so instead of looking at how hard it is to change the linear velocity of something, we're looking at how hard it is to change the rotational motion of something, how fast it is spinning. And that is going to be related to the moment that is applied through it through some time. Thinking through the two pieces of this, so mass is a part of it. If I have a bucket full of sand versus an empty bucket, it's going to be harder to get this bucket of sand to rotate. Swinging it, that's a rotational motion. For the position vector here, r cross mv, there's actually another position vector hidden in this velocity. And moment of inertia ends up being extremely dependent on position vector, even more so than mass. Resistance to rotational motion. Okay, so moment equals r cross f, r cross ma. A is dv dt. We bring the dt over. We're looking at velocities. And we're looking at rotational velocities. So in this case, velocity, instead of being dx dt or dy dt, the distance versus time that is creating that velocity, the distance is going around in some kind of circular motion. So we'll say ds dt, where s is some kind of an arc length. And if you remember, the circumference of a circle is 2 pi r. So half of that would be pi r, or just one slice of it would be theta r, where theta is in radians. That's the cool thing about radians, is you can relate the edge, the arc length, to the radius of the circle. Okay, so we're going to replace our velocity, ds dt, with s equals r d theta dt. And the symbol that this angular velocity is given a lot of times is omega. So omega is radians per second instead of something like meters per second. So miles per hour, meters per second, that would be the linear velocity. Radians per second, how much your angle is changing with time, that is your angular velocity. The angle is changing with time instead. Okay, so let's go ahead and substitute out our velocity for the radius times radians per second, our angular velocity. So r omega is equal to v, and this r omega is actually tangent to our circle. So if you look at the velocity, it's tangent. So this cross product, that's very handy for the cross product because this is 90 degrees to our position vector. So we end up with two radiuses, r squared m times omega. So for the linear velocity, remember we had mass times velocity. For rotational motion, we have moment of inertia times angular velocity. So that is what this r squared m is called. R squared m is moment of inertia. Now r squared m, this is kind of a generic form of this. And this would be if all of the mass is located at some radius from the axis of rotation. We'll go through how to calculate this quantity where the mass is not all at the same radius, but this is kind of a generic form of moment of inertia. So instead of mv plus fdt equals mv, we have I omega plus mdt equals I omega. And I is, you can think of it as a resistance to rotational motion. A larger inertia makes it harder to rotate. It is also harder to bend if you have a larger inertia. So here's just a quick concept question. We have two pendulums, A and B. A has a huge mass, 2 times the mass of B. But B has a huge string. It has a huge radius. When you look at these two systems and think about inertia, which system is going to have a larger inertia? Is mass more important or is radius more important? And if you look at this r squared, wow, the radius is much more important. And how hard something is to rotate. So think how many machines have rotating parts, camshafts and crankshafts. There's a lot of little rotating pieces in a machine. And so for energy efficiency, you want to create something that is easy to rotate. Or for civil engineering, maybe you want something that is stable. It's not going to fall over. Tipping over is rotational motion. You want it to be hard to rotate. And it's much more dependent on radius, on how far away that mass is from the axis of rotation than on the mass itself. So that's something to very much remember for the moment of inertia. So cranking through this, so here we have for mr squared, in this case, the m is actually 2m and the r is L over 2. So you can compare the inertia for case A with the inertia for case B, which is just L is the R and M is M. So ml squared versus 1/2 ml squared. So even though this thing has twice the weight, it has half the inertia. It's very, very dependent on that R. So that's this R term. This is one thing to really, really keep track of when you're thinking of rotational motion or something tipping over. It's super, super dependent on the radius, on how the mass is distributed around the axis of rotation. Very, very much so. A couple of different things for acceleration. So we went through velocity for rotational motion. Now let's look at acceleration for rotational motion. And usually acceleration, you think of dv dt. It's more than dv dt. So velocity is a vector. It has two things. It has both magnitude and direction. Speed just has direction. Velocity has magnitude and direction. And when you take the derivative of velocity with respect to time, you have to keep track of both pieces of that. So you're keeping track of how the magnitude of the velocity is changing. So if you go from like 30 miles an hour to 60 miles an hour, that's the magnitude. Then you also have to keep track of how the direction of the velocity is changing. So the direction, that's maybe I'm headed north and I turn and now I'm headed east. So my direction has changed. I could be going 30 miles an hour north and then 30 miles an hour east, but my velocity has changed purely because my direction has changed. When you're going through rotational motion, there's constantly a change in direction happening. And mathematically, that falls out of, okay, so A equals change in the magnitude times change in the direction. So you take kind of the first times the derivative of the second, and the second times the derivative of the first. You split these apart, and there's two pieces to your acceleration. You're going to have one part that is looking at how that tangent direction is changing, and one part that's looking at how the magnitude of your velocity is changing. Okay, so the change in direction, you use actually this really long chain rule to get through this, to find the v squared over r. So if I multiply it by d theta over d theta and ds over ds, you're just multiplying it by 1 and then by 1 again. But you do this, the ds dt, that turns into velocity again. So I end up with a v squared. How the angle is changing with s, d theta ds, this is like s equals r theta, circumference equals 2 pi r. This ends up being your 1 over r. And the tangent direction, how that is changing with angle, is it's being pulled in to the center. So the direction change is centripetal, like flower petals, centripetal. It's center seeking. So I'm pulling this in. It wants to go flying off in a straight line. It doesn't want to change its direction, but you have a force that's constantly pulling it to the center. You can think of planetary rotation where gravity is pulling it to the center and pulling it to the center. So this is this v squared over r, which is also r omega squared. This is the piece of acceleration that describes the change in direction of the object. The other piece of acceleration, are alpha. So this is looking at the change in magnitude. So how fast velocity is changing with time. And remember, velocity is equal to r times how that angle is changing in time. Do you see this dot above it? That is shorthand for derivative with respect to time, if you haven't seen that before. So for magnitude-wise, we have r theta dot, or r omega, and we just take one more derivative, and this is usually called alpha. Alpha kind of looks like a, so it's an acceleration, and again, this alpha is describing the angular acceleration. So instead of meters per second squared, we have radians per second squared. So it's how fast that rotation is changing with time. And if you look at what piece of this is perpendicular, okay, so r cross ma, and this is a cross product. So let's set this up. So I'm going from the center of the circle out to the edge. So radius is going in the I direction in this case. And then maybe I have my v squared over r going in the negative I direction. And you can see this r alpha, that is tangent. And so when you crank through the r cross ma piece of your moment, what you end up with for that cross product is this, you're really worried about how the magnitude of the velocity is changing. So the r alpha piece of it. So that gives you that r squared again. So you have an r squared times m, and you see that inertia coming out again. And so F equals ma, moment is equal to I alpha. And you should be as comfortable with m equals I alpha as you are with F equals ma. And those two are very similar to one another when you think about the implications of it. So moment equals I alpha. Get that equation in your mind. Moment equals I alpha. Let's just compare that to F equals ma. When you think of mass in terms of force, so you have a big mass, it's really hard to move. A little mass is easy to move. right? So you're applying a force and you're trying to get that force to move that object. Mass is resistance to that motion. It's the same idea with a moment, okay? So you apply a moment and you're trying to rotate it. So instead of meters per second squared, it's radians per second squared. And the same way you can visualize mass for F equals ma, that's the same way you can visualize I for moment equals I alpha. So if I'm trying to rotate something, if it's close to you, it's going to be easy to rotate. If it has a small r, a small I, that's going to be super easy to rotate. But if you have something that's really long, a really big R, it becomes very difficult to rotate it, to give it that radians per second squared. And it's everything from, an ice skater pulling her arms in, rotating faster because she has a smaller R. Smaller R, smaller inertia, easier to rotate, which is, it's kind of neat. You have the same mass and you're trying to move around the same mass, but you can move that mass much, much easier if you just pull that mass in around your axis of rotation. And so really that ice skater example is used over and over again because it's a good way to remember that radius dependency for your inertia. Okay, so just like you can have conservation of linear momentum, you can have conservation of angular momentum if you don't apply a moment. But the main thing here is for you to understand what this moment of inertia is. So symbol is I, and it's related to r squared m. Pull your arms in if you're on a spinny chair or something. So small r, and you're going to rotate faster. This is the case, everything from planetary motion to ice skaters. So if all of your forces are internal, you can say external moment is 0, and from your initial inertia to your final inertia, so let's say you start out with a large radius, large inertia is small omega, versus you pull in your radius, you make your I small, and if I gets small, then you speed up how fast you're rotating, radians per second. You're rotating really, really fast. Okay, so no external moment, conservation of angular momentum, and it is very dependent on your radius, r squared m. Now this is the case, this equation that we've seen over and over again is for a point mass. So if I have a tennis ball on a string or a pipe where all of the mass is at the edge of the pipe and the inside of the pipe is empty, that's where you get r squared m. For other objects where the mass is not all at the edge, so here's our pipe where the mass is all at the edge, same for a tennis ball, it's all located at that radius. That's where mr squared is. For other materials, so now I have some mass in the middle and some at the edge, differently distributed masses will have different moments of inertia, and we'll go through how to calculate the moment of inertia for different objects. It's similar to the center of mass. So like the center of mass, there are tables where you can look it up for common shapes. But before we go through and derive how to actually calculate this thing, let's look at the tables and think about what object on here around what axis is going to be the easiest to rotate versus which is going to be the hardest to rotate. So what do you think? What looks smallest? 1/12 is really small versus a third. You have length here versus radius here. But so if all of the mass is way far away, this is the hardest. This right here is the hardest to rotate. When you get some of the mass getting closer to that center, 0.5, 0.4, it gets easier to rotate. Be really careful when you're looking at these tables that you pay attention to what axis of rotation it is describing, and also solid versus hollow. Some of these pictures look very similar, but they're very different moments of inertia. And it's, yeah, hollow versus solid. Those are two very different objects. Okay, so here is the largest moment of inertia is mr squared. And here's the smallest moment of inertia, 1/12 L squared. There's some really fun Walter Lewin videos that talks about it. So you can roll things down an incline. So you start with the same potential energy, the same MGH, but one will reach the bottom faster because this also goes into energy balances. So instead of 1/2 mv squared, 1/2 I omega squared, those rotational kinetic energy as well as translational kinetic energy. So you can look at this in terms of energy balances and just how hard it is to rotate things. Okay, so 2D and 3D objects versus like a tennis ball on a string. So let's go ahead and go from mr squared to calculating it for other more complex shapes and objects. Remember how we calculated centroids. And this is r squared m versus r cross m. It's going to be similar to r cross m. So centroids was actually a moment calculation too, right? It was like taking the moment around the origin, taking the moment around 0, 0. So we would look at the distance to the center of mass. It was this r cross f kind of a deal. So we looked at how far away is it, and then the area ratio is the same as the mass ratio, same as the force ratio. And if you add this all together, you found that distance through a moment calculation, r cross f. So you have each little bit, you add up all of the r cross f's, and then you can get what radius it feels like. Okay, so instead of y times a or y times force, this is going to turn into r squared m instead of rm, is the idea. And we did the same thing for distributed loads, right? So if you're looking at the area under the curve and you have some kind of an equation that describes a pile of snow or something, so weight dx, you can figure out two things: the total force. So if I added the entire snow pile together, the total force of all of the snow, and then instead of trying to keep track of every snowflake, we just say where's kind of the center of mass, and it acts like all of the snow is acting at that one point. And you have this x times weight, right? So inertia is going to be very similar, but instead of x times weight, it's going to be x squared. We're going to add a squared term to this center of mass idea. So Chapter 5, if you go through your Chapter 5 and remember how we found centroids, finding the moment of inertia is very similar to finding centroids. Okay, so r squared versus r. So moment of inertia of an area by integration. We'll do this two-dimensional version first and then work our way into three-dimensional. And instead of r squared m, we're looking at the distance from the axis of rotation to each chunk of area or to each chunk of mass. So if we're going to rotate around the x-axis, let's say, so from the x-axis to each chunk of mass, that perpendicular distance from x is going to be in the y direction. So the inertia around the x-axis is equal to y squared dA, where dA would be just the base times the height of this element. So here's a minus x dy. The base, a minus x, here's a, times the height, in this case, is dy. If we're going to rotate around the y-axis, and remember, inertia is with respect to some axis of rotation. So you have to define what the object is and also what the object is trying to rotate around. And so pay attention to these little descriptive subscripts. So if I'm rotating around the y-axis, in that case, the distance traveled, like that r squared m, the distance is x squared, where we're going from the axis of rotation to each element. And in this case, the area, again, is just like a rectangle, right? Base times height. So the base of this rectangle is the x, and the height is y, where we probably have some equation that describes what y is. So y equals x squared or something that we can crank through integration for this. Okay, so y squared dA, x squared dA. For a rectangular area, so if we crank through this guy, so the area element is just the base times dy. So here's base times dy. Y squared goes to 1/3 y cubed, where usually the height, that's the dimension here in the y direction. So 1/3 bh cubed. That's for a rectangular area rotating around the x-axis. There's a little trick you can do, and depending on what equation you have or object, you may or may not want to use this, but we can actually take this 1/3 bh cubed and plug it in here. So remember, height, that's like in the y direction. So we can say 1/3 y cubed, and then the base here is we can call dx. X is in that base. So if you have an equation that for y, so y equals some function of x that you can plug in here, sometimes it's easier to use this 1/3 trick when integrating, versus sometimes it's easier to use this dA trick. So compare this first equation, y squared dA, with this other equation, y cubed dx. They end up giving you the same thing, but depending on what equation you have, one might be easier to integrate than the other. And we'll have some examples using each of those methods. Okay, so there's the ix and the iy, again, x squared dA, where dA is usually y times dx. Polar moment of inertia. All this is, instead of rotating around the x-axis or rotating around the y-axis, we are now going to rotate around the z-axis. So the axis coming out of the board, for which we're going from the axis of rotation at 0, 0 out to each element. So x squared plus y squared equals r squared. And the moment around that z-axis ends up being iy plus ix. So when you say x squared dA plus y squared dA, that ends up being the easiest way often to calculate the polar moment of inertia, is just to add together what ix and iy is. Radius of gyration. So for complex shapes like gears or other objects that would be hard to integrate, a lot of times the moment of inertia is just measured, or a probable statement will give you the radius of gyration, and it's similar to the center of mass. And so when you look at the resistance to rotation, it feels like all the mass is concentrated at this one radius. So it's not actually, but it behaves like it is. Just like the center of mass, the forces at the reaction behave like all the mass is piled up at that one point. It's not, but it feels that way. And for all calculation purposes, it works. So if you get the radius of gyration, instead of r squared a or r squared m, you plug in that radius of gyration, and it's not really that the mass is there, but it feels like all of it is piled up at that radius. And it's not the same as the center of mass, and it'll be just something that is given to you. If you calculate the inertia and they ask for the radius of gyration, you can get it square root of I over a. And again, this is going to be with respect to some axis. So with respect to the x-axis or the y-axis, or maybe the polar moment of inertia. So you're looking at that radius. So one way or the other, you can use that radius of gyration for complex shapes, and that's often the easiest way to solve problems. Okay, just a couple of examples. I'll go through these quickly. You can look at them in more depth in the notes. So here's a triangle. This is something you can actually look up in a table, but let's go ahead and chug through it. So remember, rotating around the x-axis, that means you're looking at the distance in the y direction. And if we go from the x-axis to some element, and the area of that element is the base times height, right? So L times dy, that's describing this element here. But what we want to get is this length L in terms of something we can integrate, in terms of y. So you can look at similar triangles here. So the length is to the height. So L is to h minus y. L is to h minus y, as base is to height. It's the same ratio. So that's a neat little similar triangle trick. But the point of it, we now have y in here. So we can get this length here in terms of something that has y. So when we plug in our y squared dA, where dA is equal to L dy, now we can plug in this equation for our length. So here's our L dy, y squared L dy, y squared L dy. And we can integrate with respect to y from 0 to h. So here's y going from 0 to h. And cranking through those limits, you get 1/12 bh cubed for your inertia around the x-axis. So there's one example of sometimes you have to be a little bit clever in defining your element with respect to something that you can use to actually crank through that integration. Here's an example polar moment of inertia. And remember, the polar moment, that would be rotating around the z-axis, but you can get it from adding together the x and the y-axis. And sometimes one is easier to get on the other. So in this case, it's probably going to be easiest to define our element as just a circular ring at a distance. We'll call it u. So dA here is going to be the circumference times that du. And we can crank through u squared dA. So here's our dA. There's our polar moment. It's symmetrical. And so if we want to get Ix and Iy, we know that these two are the same, and we can get that just straight from our polar moment. So we just divide this by 2, and we have Ix and Iy. So with one fatal swoop, we have the polar Ix and Iy for this. Here's one more example. A lot of times they will not give you an equation, and you have to actually look at the dimensions of the shape to create your own equation to describe it. So this shape, you can, it's just a linear line, right? Y equals mx plus b, where the slope is the change in the height over the length, h2 minus h1 over a. So hopefully it's not too difficult to create an equation here. And then for Ix and Iy, you're going to think through the easiest way to define your element. So let's go ahead and think through this element for dx. Okay, so remember, dx means that we're going to be rotating around the x-axis. So if we're going to rotate around the x-axis, that means we're looking at the distance in the y direction and then some element in the y direction. And for this one, if we're up here at the top with this triangle, that's going to be one element, versus if we come down here, then it's just a rectangle. So we'd have to actually define two different systems there. if we did it through that method. And this is where that little trick with the 1/3 comes into play. This is going to allow us to define a vertical element for our inertia around the x-axis that will make this a lot simpler to solve. So using this 1/3 trick, we can define our element as simply that height, which is going to be our entire equation, right? So we're going to plug this entire equation in here for y and then integrate with respect to x. So that's, remember that 1/3 trick because that can really help you. So here's our inertia with respect to the x-axis here. For the inertia around the y-axis, that ends up being a little bit easier. So once again, that means we're rotating this object around the y-axis. So our distance is perpendicular to that, x, and we have that same element, but now we can just plug it straight in there. So we have our equation for y times x squared dx, and we can get the inertia then around the y-axis. If you have an area that's bounded by two lines, inertia is additive. So what you're going to do is define your element as what's on top minus what's below. So again, you can think of this guy as just a rectangle where the height now is the equation, this y2 minus y1. It really does help to draw in that element and think about what your dA is to integrate and crank through these. If it's symmetrical, then you can look at just one side and multiply that one side by 2. I won't go through all these examples, but they are in the notes. So let me know if any of these gives you trouble. And if there is any particular problem you would like to see a video made of, just let me know, and I'm happy to make some more videos for this integration method as well. Parallel axis theorem. So a lot of times in tables, you're given the moment of inertia around an axis that goes through the center of mass. But let's say I don't want to rotate it around the center of mass. I want to rotate it around maybe some new axis, right? So if I have the inertia around here, but then I actually want to rotate it around this different axis instead that goes around the edge, and I want to figure out what the inertia around that new axis is. That is what the parallel axis theorem is for. And what we're going to do is we're going to take the inertia around the center of mass and we're going to relate it to the inertia around some new axis. So for this one, we'll be trying to rotate it around this new axis AA. For this distance y, so from the axis of rotation to each little element, and you can split this distance y into two distances. One is how far away the center of mass is, and then from the center of mass, that last little chunk up to each element. If you crank through this, so you get y prime times y prime squared, what this turns into is the inertia around the center of mass. So that's the piece that you'll get out of the tables. For the other chunk of it, the d squared piece of it is going to turn into a d squared, where d is the distance from the center of mass to the new axis of rotation. And this middle term here actually goes to 0, because if you think about it, we're integrating over the entire thing. So half of the area is above and half of it is below. And when you don't have the squared term in there, what is above and below end up canceling out with one another. That's the definition of center of mass. So this central piece goes to 0 and we don't have to worry about it. So that's the real important here is we're taking this around the center of mass. So this is the center of mass here. Whenever you see a bar over the top of something, it's talking about going through the center of mass. So this is the inertia around the new axis is equal to what it is around the center of mass plus the area of the object and distance squared, where distance is from the old axis to the center of mass. And it's as you get farther and farther away from the center of mass, it gets harder and harder to rotate, is what this equation. But remember this because it can be used with tables and is very convenient for finding the inertia around that new axis. Here's a parallel axis example. So let's say we have the moment of inertia around this green axis, around the center of mass, but we want it instead around this yellow tangent axis. So what we would do is we would add what we find in the table around the green axis, the area of the circle, pi r squared, times the distance to this new axis. And then we would have the inertia around that new axis. So this is a very handy thing to go back and forth between what axis. Here's another example. So let's say in this case, maybe the table gives us the inertia around the yellow axis, but what we also actually want is what it is around this green axis. In this case, you can just rearrange this equation. So we have green is equal to yellow minus blue. So we're just bringing that AD squared over to the other side here. And we can go back and forth from the yellow to the green or from the green to the yellow. So you can rearrange that equation too to go back and forth between inertias around different axes. These tables you can get, there's good tables in Wikipedia, there's tables in the cover of your book if you got that, or if you just do an image search, you'll be able to find tables like this. When you're using these tables, be very careful to grab the right inertia. So look to see how this thing is labeled. So when this has a bar across the top, that means it's something through the center. And then you look for that little X. So this would be the inertia around this yellow axis. Or the other centroidal one, that would be the inertia around this green axis. And this one actually gives us the inertia around the base of it. So see how that just has X, but there's no bar on top. Or the inertia, let's see, what color haven't we used yet? If we look at it around this axis, that would be this. And the centroidal moment, this very last one, okay, so that would be like the axis coming out of the board in the Z direction, how hard it would be to rotate around that direction. So this last one, that would be around this third direction coming out of the board. So it's really easy to grab the wrong equation here. So really study how these lines are labeled and how the inertias are labeled on these tables when you're going through those. But for common shapes, you can usually find what you need in the tables. Okay, sample problem. So what we're going to do is determine the moment of inertia of this shaded area with respect to this yellow x-axis. And you can do this in parts. So first we're going to get the inertia of just the rectangle around the x-axis. And because the semicircle is a hole, we will subtract off the inertia of the semicircle around the axis. These are common shapes, so let's jump over to the tables. If I look at the rectangle, it has the inertia around this yellow axis already, so we can just plug that 1/3 BH cubed in for the rectangle. For the semicircle, unfortunately, we're going to have to use the parallel axis theorem for this one. And remember, the parallel axis theorem goes from the centroidal axis, not from what the tables are giving us here. So this is actually going to turn into a two-step process. From this axis to centroidal, and then from the centroidal back down to the new axis. So this is going to be, let me draw it in here. We're going to go from this top axis to the centroid, and then from the centroid to the new axis of rotation. So we'll have, let's call this A, and we'll call this the centroidal that has the bar over the top of it, and then we'll call this last axis IX. So if we have the inertia around AA, which is what is in the table, and that is also related to, I'm going to call this first distance A squared. So we'll go from AA to the centroidal axis, right? So that centroidal axis is equal to what is given in the tables. And then we can go from the centroidal axis to our new axis that we actually want. And we can't go straight from A, because remember that parallel axis theorem we derived, it only works around the centroidal axis. That's where that middle term canceled out to 0. So we can't skip a step here. We have to go from A to the centroid, and then from the centroid to the new axis. So two different steps here, but I guess that's not too bad. Okay, chugging in numbers, the rectangle, that's at 1/3 BHQ, so you can chug in dimensions for B and H. Keep in mind, inertia has units of length to the 4th. For the half circle, first we're going to go from the yellow that's given in the tables to the green. So that's the first jump that we make using that parallel axis theorem. And then we're going to go from the green to the blue. So here is finally the inertia around the blue axis. And the value here for the entire shape together is what the rectangle was minus what the semicircle was. So there's the inertia of the combined shape around the axis. So it's hopefully some of this is starting to look like the center of mass calculation. So that was using integration to find it, and also chugging this through parts. Okay, let me know if you want to see any other examples worked out in a video. Next up, we're going to look at beams and Moore's circle for principal axes of rotation.